Overview from our May meeting of last year to bring new students who have started the project up to speed with kind of the overall philosophy, and then go into the details of what we've been working on recently. So if you have any questions, please feel free to stop me. I can't. How do I advance the page? Okay. So the objective of our activity is to develop a multi-physics-based simulation of the entire upper Colorado watershed to run on the Yellowstone supercomputer. And when we wrote the proposal, we had to think big to use a supercomputer. So this is the scale of problem that we came up with. And the high-level overview of what we're doing, there'll be a lot of input pre-processing that will need to be done before we can run. That's mostly land surface data, estimation of channel cross-sections for hundreds of thousands of kilometers of channel, and processing 30-meter DEM for a 288,000 square kilometer watershed to produce a unstructured mesh with high resolution in places where we need it, such as in high altitude areas where slope and aspect are important for snowmelt, and also near stream channels where the groundwater gradients need to be accurately modeled to get the flow from subsurface to surface correct. And then forcing inputs. There's not enough data to drive this model in instrumental records, so we're going to use WRF to force the model with radiation, meteorology, and precipitation inputs. So the input processing stream that we've developed starts with the USGS DEM, uses TAUDEM to produce a delineated watershed and identify streams. That information is then used with catchment stream geometry and connectivity. We bring in the National Hydrography Dataset water body so that we can identify lakes that have been pre-identified. QGIS and ArcGIS are used to process the data into a format that we can use to generate the unstructured mesh by topological polygons and lines. We can't use QGIS for the entire process because it lacks a key feature that ArcGIS has in terms of cleaning up the vector data set and reducing its resolution to a point that doesn't generate a bunch of ridiculously small triangles. After we get the topological polygons and lines, we run a program called Triangle, which generates the mesh. And from the 2D mesh, we then can take StatsGo data for soils and combine them with the custom code and download the land use data from the U.S. Geological Survey to assign soil and land use properties to our mesh. MEDIS is a method for doing, we use it for a first cut at partitioning the job amongst different computer elements. But notice that we were using the topographic information to help partition the different mesh elements between different processor nodes. So related nodes will be most likely to be on the same processor node. And mesh elements that are far away could be, on very different processor nodes in the supercomputer. The stream data are used to just develop a 1D channel network. We've done some very nice research on geomorphology and scaling laws to estimate bankful channel cross-section properties, and that will then be used for the symmetry of the channels or the Thal-Webb profile. So we start with the USGS DEM. We run TAUDEM, it gives us subwatersheds and streams. The subwatersheds are kind of our basic computational unit, and there's a lot of no-flow boundaries around those, so we can take advantage of that to minimize communication amongst cores or different nodes.
Are you actually doing the parallelization on a sub-watershed basis?
No, not exactly, and I'll get into that in a moment. But in terms of...
I guess one of the things, I guess right now, one of the issues we have with TOWDEM is that where you have a very short stream segment, it sometimes makes really small subwatersheds. And
we delete them.
Okay, I guess we've been trying to figure out a way to, well, we've been changing TOWDEM to not necessarily have the subwatersheds only associated with stream segments. And I don't know if that's something you're interested in or not.
Well, I'm not sure. I wish Bob were here. You weren't on the line. Bob Stanky had to take a child to the dentist this afternoon, so he's not on the line. But he has come up with a way to get rid of those really small channel segments and delete those small watersheds. I don't know the details of it, but he should talk to you about that. Did someone just join? Or did someone just drop? I think it was a drop. Any other questions before I go on? Hearing none, I will proceed. So the National Hydrography Dataset water bodies are then merged with the channel network to form a set of arcs that close the boundaries of watersheds and water bodies. And the water bodies are just part of the channel network. But then there's a lot of resolution in that output that we don't need. So we use ArcGIS to thin the polygons and reduce the number of points. Of course, we lose a little bit of accuracy in watershed areas, et cetera, but the changes tend to be pretty minimal. And then we run this set of polygons into Triangle and say, generate our mesh for us. And it does that. And you can see that it omits the lakes, because we don't need mesh, we don't need elements inside of the lakes. And we get a pretty nice looking grid. Some of the triangles are up to, approaching half a square kilometer in size. And they tend to be in areas that are topographically not very important. And on the boundaries and on watershed boundaries, which tend to be the upslope areas, we get a little bit higher resolution. And then METIS, which is a...
So there's a question here.
Sure.
So, Dr. Ogden, this is Otto. I'm wondering about like the water bodies here. Like, you're representing them as like part of the mesh or the nodes. How they're represented here?
So these holes that you see in the triangle output, those are water bodies. The little small ones are neglected. We have a threshold. You can see that there are some water bodies on that ArcGIS polygon set that are pretty small that disappear when we run the mesh. We've decided that very small water bodies we will ignore. The big ones, like the one that's up near the top of this figure, if we look here, there's a lake. And those will do level pool reservoir routing through those, and the water level in the lake will interact with the water level in the adjacent mesh elements.
Okay, good. So how do you connect them with the rest of the network? Like, is there an inlet and outlet point, like a node for them?
Yes, there is.
Okay.
And we'll assume, I think we assume a critical depth assumption at the outlet of a lake.
Okay. So I'm interested in knowing like what kind of data you want for these water bodies, and later we can talk like off the line, I believe. So I think how to serve their data to you guys if you need it or if we got it at some point.
Well, there's several different. There are uncontrolled water bodies that just have, they serve as a head boundary condition for upstream channel links, and they serve as a queue of time boundary condition for the downstream links. And then there are controlled reservoirs that actually we're developing a water management layer to release water from.
Okay, all right. Thank you.
So METIS is a partitioner. It takes a stab. It uses watershed boundaries to break up the mesh into approximately equal number of mesh elements that will be sent to different processors. And you can specify how many processors you have. So like this has 1, 2, 3, 4, 5, 7 or 8, 7. 6. So it, it was given 6 as an argument, and that's what it told, how it partitioned the mesh. But this is the first cut. After this, we have other software that will take over the partitioning problem. So it's a large scale. That's the entire upper Colorado River Basin. The area I was just showing you is that little area in red up at the top where the arrow is. And so to give you a problem of the scale, what's actually displayed on that graphic is the channel network. At this resolution, the pixel size is so big compared to the basin that all you see is channels. Because our drainage density in the watershed, according to the blue lines from the USGS, is about 3 kilometers of channel per square kilometer of land area. So it's an awful lot of channels that we have to simulate. Our forcing input will be the data from WRF output, temperature, humidity, wind, solar radiation, liquid precip, and snowfall. We'll have water management, which will be reservoirs, diversions, and irrigation. Forcing inputs could be historical data, outputs from other models, stochastic generated time series, or opportunities for collaboration with others. But we're planning on focusing on WRF output at this point that Cord Strong's been running for us.
Hey, Fred?
Yes.
Rosenberg. What time scale and what time extent are you going to be running the model at?
Time scale and time step?
Yeah, or time step and time extent.
Well, the time step will be seconds. The duration will be decades, which sounds ridiculous, but we have a supercomputer. And the seconds is required because we're using explicit routing.
So when you go to validate the model, what are you going to be using to validate it, or at what scale, spatial and temporal scales, are you going to be looking to validate the results?
Well, validation is a word that I don't think can be used in the context of this kind of modeling. I think what we are interested in is, are we accurately simulating processes? And if we change something from one simulation to another, does that change, is that accurately represented in the difference in the two forecasts? You've got to think of it more like you would a climate model. The calibration trap is hard enough at a really small scale. This scale, I think annual water budget, that kind of thing would be, if we go back and simulate historical periods, that's what we can do. Does that make sense?
Yeah. So in simulating historical periods and trying to validate it at an annual scale?
Yes.
Okay.
I think maybe seasonal. We're going to definitely be emphasizing snowmelt, so we want to try to get the snowmelt runoff quantities approximately close.
Okay.
Thanks. That's a really important question. Thank you for asking it. So the simulation is serial in a way with, preset forcing inputs first, and then we'll do infiltration. The water that doesn't infiltrate will go into the soil or become surface water. The surface water will flow into the channel network. Channel network interacts with the groundwater, and then the water management layer kind of controls what's happening at the managed points in the channel network. Now, that's a little bit of a simplistic diagram because there's options and things that aren't shown there. In the output visualization, we'll be generating HDF5 or NetCDF files and use ParaView to view them. So far, we've been using HDF5 files, and there will be opportunities to collaborate with other people who are interested in looking at visualization. One of the things I'm really eager to see, if we take a multi-year simulation, we should be able to see the snow pack migrate down the mountain in the fall and then back up the mountain in the spring. We should be able to show areas where, and we'll have to zoom in to do this, areas where the water table is near the ground surface or where it's far from the ground surface, things like that. We're probably using the PINS approach of Google. We might be able to visualize in pretty high speed an annual hydrograph in the runoff cycle. The status of the project, the TOWDEM, a lot of the workflow stuff is pretty well in hand. Using TOWDEM and the QGIS and ArcGIS and Triangle to produce our mesh, that's pretty well done. The code to process soil and land use properties, we haven't really started on that. It's not going to be that hard of a deal to take land use polygons and map them into our mesh. That'll be pretty straightforward. Using the standard USGS indices, we'll be able to assign the land cover type pretty easily. And we're using the same exact classifications that NOAA MP, the land surface ET scheme that we're coupling with, uses. So that's going to be pretty straightforward. The soils and land use, we have, the soils data, you know, Jim's student gave a nice presentation last fall on that. There's a lot of data there that we don't typically use. Right now we're going to be assuming a one-layer infiltration model using an improved scheme that we'll be talking about during the cyber seminar in April, so I won't talk about that right now. But it does a very nice job of coupling the land surface to the groundwater table in a mass conservative way. We have created all the code to do the channel network processing, and that runs. The code to produce the channel bathymetry, I'm waiting on a master student to finish up his analysis of the scaling relationships, which is, he's almost done with that. The coupling with WRF is something that we have not done yet. We're in the process of trying to hire another postdoc to work on that. And we have, the search is closed. We have 2 pretty decent applicants that we're getting reference letters for. And the water management model layer, we have a pre-doc, Yoshiyuki Ishikari, who's working on that.
So Fred, when you say coupling with WRF, is there actually going to be feedback from this model to WRF, or is it going to be a one-way thing?
One way to start, but the long-term goal is definitely 2-way.
So, I mean, I guess following on that, could you explain what you mean by water management data being a forcing input? How's that going to work? Or what is that going to look like?
Well, I think it's the understanding of how the reservoirs are operated. What are the rule curves? And I'll talk a little bit more about that, Dave, in a minute. The snowmelt serial code, because it's a point process, you know, we have the Fortran. We're going to use the Fortran. We have a wrapper that we'll call it from the C code. The rainfall serial code, I don't know exactly what Bob means by that. That's really part of the WRF input. Infiltration code is running. We have a paper submitted on it. Coupling with NOAA MP, which is the evapotranspiration code, we've developed a wrapper. We can call it. We just haven't, because we haven't developed the code to generate the land use IDs, we haven't been able to call it in a meaningful way. Channel code is done. Groundwater code is done. They all conserve mass. The water management code right now is 0% done. Zen is working with some MATLAB stuff, trying to back out operation rules for some reservoirs that don't have very good operating data. The serial code, the model runs serially on a single desktop. That's been done for a couple of months. Parallelization, we've just gotten started on in the last couple of weeks. We were, a month ago, ready to charge off and start putting in a bunch of MPI calls. And Craig Douglas put the brakes on our operation and said, you don't want to do that. We want to try to do better optimization while we're parallelizing.
Can we go back to the water management code for a second? You mentioned that a student was trying to, I guess, back out the operating rules or deduce the rules. I'm assuming that's from what you observed were the observed releases?
Yes. And I'll show some results on that in a minute.
Which reservoirs are you working with?
Right now he's working on Fontenelle.
Okay. I think I may be able to give you an easier suggestion for how to do that.
Okay, great. Output visualization, we can write these HDF files, 5 files, and visualize them with ParaView. That, I think, is the end of this part of the presentation. I have to switch to part 2. Now, where's is the stuff from Zane in this part? Okay. All right. View. So the code parallelization, that's the last page. Thank you for correcting me on that. Okay. Channel network and mesh generation done. Green and F redistribution coupled with Talbot Ogden is done. We've run the serial model on the entire Upper Green River Basin. We have wrappers for NOAA MP, UED, and where we worked with some WRF output, but we haven't finished anything about ingesting that yet. Water management is in progress, as is code parallelization. So the way you can think of this model is it's a bunch of processes that talk to each other by state variables. And if you think of it that way, you can start to cast it in an object-oriented framework. And it turns out when Craig Douglas said stop writing MPI code and think more carefully about what you're doing, he was hinting that we should consider thinking about this in more of an object-oriented framework, which I am not a C++ guy, but Bob Stunkey is, and Bob Stunkey very quickly saw the benefits of doing that. The coupling between the surface, groundwater, and channels is done. We uncovered some issues. When you go to an unstructured mesh, you can have places where it creates artificial pits and dams. We have done some pre-processing to eliminate those, and it sometimes comes down to maybe a channel begins at the vertex of a mesh element, which is a triangle. We had to make the code smart enough to realize that that's going to, the outflow from that mesh element is going to go into the channel at its upstream end. So the runs that we've done on the Upper Green River Basin, now this includes Fontenelle, doesn't it? Yes, it does. Fontenelle Reservoir is this one right here. And there are some other reservoirs up here. Now, there are glaciers in this area. These water bodies up here are actually glaciers or glacier-fed lakes. And so running on a single CPU at this 1,220 square kilometer size with 1,572 kilometers of streams gave us 36,000 mesh elements and 14,000 channel elements. And that run happened more or less at about clock speed, 0.6 to 0.8 of wall clock speed. So it's slower than the wall clock. Faster. Okay, so we could do a 10-hour run on a single CPU in about 6 or 8 hours. That was with TO. The improved infiltration scheme that we come up with runs about 20%, 20 times faster. So we will be able to run that a lot faster. These are some example ParaView output showing surface water depth overlaid on topography and groundwater depth on the topography. Integrating UEB grid snowmelt model will be done by a wrapper, as I mentioned before. Their post-process, or their serial processes, so each mesh element will call its own version of those. This is some of David Rosenberg. These are some of the results that Yoshiyuki, who goes by the name Zen, has come up with for observed in simulated releases from Fontenelle Reservoir. Because
on the y-axis?
The y-axis is the water level. On the upper graph, it's the water surface elevation. And in the bottom graph, it is the release, the flow rate.
Okay.
So he struggled for a while, but he came up with a way to infer what their operating rules were. And he talked with some folks at the Bureau, and the rules are not well defined.
So, I mean, I guess the releases look to be about the same time between what you're labeling simulation and data, but the water level change is lagged by about a month between simulation and data. So what's going on?
I don't know. His initial conditions look very different. And I don't know why that is. This might be just a subset of his simulation, I'm guessing. He probably did a multi-year and just blew up one year. And that he's carrying over some errors from a prior year's simulation on his water level, it looks like.
Yeah, but the reservoir level should affect the release too. Meaning it's a multivariate relationship.
Yeah, and I'm not in a position to answer those questions because I didn't do this work.
Oh, okay. Yeah. But you guys did talk with the reservoir operators.
Yes, he did. In fact, a few weeks ago, he spent a week up in Pinedale talking to people who operate some of the smaller reservoirs.
Right. Okay. Maybe we should talk offline a little bit more about that, because I think I could probably further help you get an operational scheme in the model that will better represent what they're doing on the ground, and that won't send you down a dark, long tunnel of trying to regress the fit and figure out from the empirical data what they're trying to do.
Okay, that'd be great.
In the end, it's what they're trying to do, which is really the most important thing, not what they actually did.
Okay.
I'm serious.
I agree. Yeah. And
what they actually did is affected by probably 5, 6, 8 other variables that you probably don't have and are not including in your analysis, and you never can. They're just unmeasurable.
Yeah, I believe it. He's a very hard worker. I'll have him contact you. The other thing, as you suggested, we have purchased a license for Riverware.
Mm-hmm.
And we are going to have that up and running in the next week or so.
Okay, cool. So we can also take that apart, and you can maybe even just pull out the rules that are in there and what do I want to say? And use the logic that's coded in those rules, and that's in essence, the verification of the model. It has nothing to do with the empirics of trying to match some observed outflow.
Okay. I will definitely have him contact you promptly. So, parallelization, we've decided to use this. Do you want to talk about this, Derek? Okay. I'll be happy to answer questions. Okay, so Derek Serwinski's in the room. He's a postdoc working with Craig, and he can help answer questions about this, because I am not an expert in this stuff. So I'm switching into Bob Steinke mode. We're using Charm++, which is a mature, about 20-year-old system for parallelization. It's a library, and it has a master controller that is very smart. It was developed by the Parallel Programming Laboratory at the University of Illinois, Urbana-Champaign. It's based on the design of another system called Lynda, which is proprietary. So it's kind of a open source version of Lynda, and it's open source for non-commercial use, research, education, etc. If you wanted to use it for a commercial project, you'd have to pay a licensing fee to UIUC. I have no idea how much that is. And it causes me a little bit of heartburn to use something that has this kind of license, but For right now, this is purely a research tool. I don't think we're going to have trouble. If we did, we could look at purchasing Lynda or switching to something else. The code required to use it is not that demanding. A lot of our numerics are still in C, and it's at a low level. It still looks like a model that we can all understand. It's only at the very top level that this Charm++ comes into play. Is that right? Charm++ implements a special kind of C++ object. The objects are relocatable by the runtime system. So Charm++ does the load balancing for us. Every mesh is an element. It's an object that has its own set of state variables, and they're not really function calls, but you can access them in a way that causes them to operate on themselves or with their neighbors. So it does relocation to automatically perform repartitioning to optimize communication and load balancing. So Charm++ is going to keep adjacent nodes or adjacent elements in our mesh on the same node to the extent that it can. Another nice feature of it is it automatically provides checkpointing, because it has the ability with what's the term when it forces everything to line up in time? Barriers. It has barriers, and instead of updating the state variables and forcing a wait, it can write those out to disk. And that's an important part of this code because of the runtime limits that Yellowstone has. A job can only run for 8 hours. So at 7 hours, 40 minutes, you have to write everything to disk and then restart it up again. All method calls to objects are location transparent. So if one mesh element needs to do something with another one, it places a call to an MPI call to this Charm++ system, and it passes it on to that other element no matter where it is. If they're on the same node, it's a very fast communication. If they're on different computational nodes, it'll be slower.
One other advantage with that is if this happens frequently, it will move the data so that it's all on the same node. So it will actually minimize communication over time, and it learns.
That was Derek Serwinski, for those of you who haven't heard him speak before. So it's object-oriented. The method call is...
So it sounds like it takes care of the MPI stuff for you. You don't have to do anything, is that right?
That's correct. So it's very efficient for us to use for that reason. All the threads are implicit. You don't have to write your code to understand what threads are, which is a very nice feature. It just creates a pool of objects and a pool of work to be done in the form of undelivered messages, and it sends them out to whatever processors it wants. The method calls on a single object are serialized, so only one thread at a time can be calling a method on a given object. But if you've got 8 cores or 16 threads on your CPU, you can run 16 objects simultaneously. And the barrier and reduction primitives are available just like they are in MPI. So the barrier says, okay, I want everything to sync up on this time. So if you have different domains of the model that are using different time steps, say every hour you want to sync everything up, you can do that. Or reduction primitives are available where you can query all of the objects and say, what is your current time step? And then you can get that information back and say, use a min operator to say, oh, this guy over here has the smallest time step, so we're going to run all of these at the same small time step. We have 2 methods that we've identified for parallelizing the code. In the first one, across the interface or a boundary between 2 mesh elements, both of those mesh elements know the head condition of their neighbors and the head condition in their own element. So they can each calculate the same flow across that common boundary. Because you would send the groundwater head and surface water depth to your neighbors, and then you would receive the updated groundwater head and surface water depth from your neighbors. You would calculate the flow rates, and if you have to limit them, say the overland flow rate times the time step is more volume of water than is available, you might have to limit one of those and then inform your neighbor that I just limited my depth flux. And there's a potential race condition that could exist there, but the way that this is set up, there's if a flow rate is limited, a message is sent over, and if that message arrives after the other neighbor calculated its flow rate, it would supersede it before updating its system head and surface water and groundwater state variables. But the thing is, you're calculating all the fluxes across all the boundaries twice in this method. In method 2, you pick one. Say the mesh element with the lowest ID calculates the flux across its boundary with its neighbor with a higher ID, sends that message over, and then the other one can update its state, and then limit, and if it has to limit, it communicates back. So you're reducing calculations, but you're increasing communications. And because increasing communications is usually more expensive, we probably will do method 1. We'll be able to try both of these different schemes. And that's the end of the presentation. Kind of got into the nuts and bolts there at the end, but that's where we're at.
Thank you.
Well, it's good to get into nuts and bolts.
Sorry?
It's good to get into the nuts and bolts.
Yeah. It is good to get into nuts and bolts. But we are, literally these last 2 slides are things that Bob identified last week as possible problems and possible solutions to those problems.
One thing we should probably point out with Charm++, we're sort of still in the honeymoon period with it. So everything seems perfect and we don't know the problems yet. So if it sounds too good to be true, that's probably because we're still learning. Or it could actually be too good to be true. We don't know yet.
We're hoping that since it's 20 years old and it is pretty widely used, we think we're pretty much going to have success with it. The fact that it does the load.
Have you got a sense what it does for you in terms of, I guess, speed up? I mean, when you run on, say, 100 processes versus 10, do you get a 10 times speed up in terms of wall time?
It's too early to tell. We're still getting test codes run.
Yeah. I don't think it won't be linear, but it should be some exponent, hopefully closer to 1 than 0. But one of the things, the cyber seminar we're giving later on our new improved infiltration code, we found that Talbot Ogden was taking about 60% or 70% of the CPU cycles. And by combining gradient redistribution for the surface infiltration and Talbot Ogden for the groundwater dynamics, we got about a 20 times speed up. So that run that we said earlier was taking 6 or 7 hours to do 10 hours of simulation. We sped that up by a factor of 20. That was a really big improvement. We have on the whiteboard over here a number of speed ups we need. We need 1,000 times real time to simulate a decade in half a week. And our expected parallel speed up that we think we might be able to get is 8,000 times if we use 64,000 cores on Yellowstone. So that would mean we would be able to run a decade in a quarter of a week.
In 2.5 years?
For 10-year simulation, that's not bad.
So Fred, I'm just curious, are all your modules for the EdHydro model running at the same time step? Or are they different?
No, not necessarily. Snowmelt, ET, those things could be called once an hour probably.
Uh-huh.
The hydrodynamic stuff, not necessarily. Groundwater will probably run at a different time step than surface water. And we've got that running that way. And we use accumulator variables to handle the fluxes between model components that are running at different time steps.
Okay. How about for the water management stuff? What time step are you planning to run there?
I think that could be hourly. I don't think it would be higher resolution than that. Do you think it would need to be?
If you're just doing diversions and reservoir operations, I think you could even go to daily, probably.
I think maybe hydropower would be the case where you'd probably want to do hourly.
Well, hydropower definitely, but it didn't sound like you were planning to support that use.
Oh, it'll have to be in there. I don't know. Flaming Gorge, I'm sure, has a hydropower plant, right?
It does. So does, I'm sure, Fontenelle, but it's just a question of whether the model is going to represent it or ignore it.
No, it needs to be. It's just another release. I don't know why.
So for hydropower, I think hourly would probably be appropriate. Maybe you go down to 15 minutes.
Yeah, we could do
and
that.
For flood, if you're going to do flood operations, then hourly, 15 minutes, maybe 10 minutes would be appropriate.
Okay. So Zen is, kind of working with his MATLAB code to try. He's really just trying to get his head around how the whole system works and what the number of different kinds of operations there are. And he's working full-time on our project now. And, our hope is that at some point he will be able to work with Bob Stunke, who is our primary programmer, in implementing this management layer. But of course, we'll need a lot of help.
Okay, we should probably talk at some point. And also, as Otto was alluding to in his question on the matter of handling the data or serving the data to y'all, if you're needing help there.
We are. Well, yeah. There's a lot we need to talk about with data. I think the way this will work in the context of what BYU is doing will be similar to what they're doing with Geisha, which is there's a pre-set up model where the mesh has been generated, the land use and soils are there, and then some pre-built scenario, it could be a future climate scenario or a land use change scenario, would be available for someone to run using the web interface. And then the other interesting thing comes, and you could have a different management scenario as well.
Mm-hmm.
So I think, I remain confident that by August we'll have this thing running in parallel with the calls to UEB, WRF, and not the calls to WRF, the calls to NOAA MP, UEB, and ingestion of WRF output by August. The water management layer, probably not by August.
Fred, this is Norm. We've got our Google Maps engine up and running, and we also have ParaView. We'd love to get a sample mesh if you could ship to us that we could play with exporting that from ParaView to the raster images of the size we need to put on the Google Maps engine. So
Bob hasn't sent you anything yet?
Not that I'm aware of.
Okay. Well, that small green river mesh, we can send you that.
That'd be great.
HDF5 file with a bunch of groundwater heads and surface water depths, like the images I showed earlier. That would be great. I'll make sure he gets those to you by tomorrow.
Thanks.
But we've ramped up. Craig has Derek and his student Luke Wan involved. Craig has been coming over for meetings regularly and code reviews. So we're really ramping up on this parallelization stuff. Any other questions?
Thank you.
Okay, well, thanks everybody. Norm, anything?
Nope.
Okay.
That's good. Thanks, Fred.